Clément.
Attends, il n'est pas reçu. Peut-être partager.
Clément, c'est bon bah. C'est con ça.
C'est mal, ça marchait tout à l'heure. Bon, si je ne l'ai pas ici, c'est pas grave, mais...
Oui. Ah.
Je pense que c'est le câble qu'il faut.
C'est le câble, ouais. C'est pas la première fois que ça me le fait en plus.
Ah.
Ah, c'était le câble. Clément, c'est toujours bon. C'est toujours bon. Oui, mais ça partage toujours ou pas?
Okay.
Impeccable.
Okay, it works. Okay, thank you a lot. First, thank you for inviting me to your workshop. I'm MATHIEU. I'm a nuclear physicist from lab not far from here, the Laboratoire de Physique des Deux Infinis in Bordeaux. Okay, the goal of this presentation is not to do a proper full lecture about radiation matter interaction, but just to give some basic knowledge about this subject. And I will give a focus about radiation protection because we want to irradiate some material in the project we have. And it's important to be aware about that. And I will obviously focus about material irradiation. First, let me introduce some terms. Ionizing radiation are emitted by the nuclei of atoms. So you have, for instance, carbon-14, which decay in nitrogen-14. And this process emits particle or radiations. So we can produce ionizing radiation in artificial processes, for instance, with accelerator, but there are some natural processes also which do the same thing. Radioactivity is something a little bit different because this is the decay of an unstable nucleus into another nucleus emitting radiation, and radioactivity is a natural process, but it can be also artificial. We can produce artificial radioactive nucleus. So ionizing radiation can come from various sources. Some of them, as I said, are natural, others are artificial. Our own body is radioactive. There are some cosmic rays. We breathe radon, which is a radioactive gas. You have some artificial sources, for instance, accelerator or X generators for medical application, for instance. You have whole sources coming from the nuclear industry, the fuel, waste, etc. Ground around us emits also radiation. So it's important to understand that ionizing radiation are everywhere. So if we speak about radioactivity, I just show you what we call the nuclide chart, where you have the number of protons in your nucleus and here the number of neutrons. All the elements, we call that, we know naturally on Earth and are on this black curve. But you can have different nuclei called isotopes, which are not stable and which try to go back to stability by decaying into something else. So you have a color scheme depending of what type of radioactivity the nucleus will undergo to come back to stability. Okay, in nature, you have only few of these radioactive nuclei which exist. All this big area here and there are produced in artificial process. Some stuff about radioactivity. Important to know is about the half-life of the process. Because it's a decay, it's a statistical decay, a Poissonian distribution. So you can define the half-life by the time given to for a given number of nuclei to lose half of this quantity. So in this process, you can see that the decay is slower and slower as the time passed. The half-life of the different nuclei are very, very different. You can have half-life from nanoseconds to billions of years and higher. And we use a specific unit, which is 1 becquerel. It's equivalent to 1 decay every second. So, what is the problem with ionizing radiation? Why do we want to protect us from this ionizing radiation? It's because they pull out electrons in the process. You can have two different processes depending of the particle concerned. You can have a direct process which happens systematically. For charged particle, for instance, for alpha particle or for protons going in matter, it will knock a lot of electron in the array. If you have an electron, it's a light particle, but it will do more or less the same thing. It will knock out a lot of electron in its path. On the contrary, when you have a neutral particle, it's an indirect interaction which happens randomly. I give here the example of gamma rays. So gamma rays can penetrate through matter. At one point, it can interact with a nucleus and do something, for instance, a scattering, and again, knock out an electron, which will knock on the other electron, etc., etc. So by stripping some electrons, this ionizing radiation will destroy chemical bonds, so molecules, our molecules, for instance, and that's the problem. And I can precise that they can also collide with other nuclei and do other effects. We will see that later. So if we speak about radiation protection, there is 3 basic principles to protect ourselves, which is called time, distance, and shielding. It's very obvious. Time, it's very basic. The irradiation is proportional to the time. So if you want to reduce your irradiation, just spend less time with the source. The distance, more or less, the irradiation depends on this type of 1/, distance squared law. So if you are far from the source, obviously the danger is lower, and when you get closer, it's rise quite sharply. Okay, there are some exceptions, but a lot of ionizing radiation works that way. It's very basic. Do not come close to the source. And something a little bit more complex, it's the addition of shielding to protect us from the source. And in fact, it depends on the particle we are talking about. And the efficiency of the shielding can depend of this particle. From, as I write, from very effective to completely useless. So it's important to know what we are doing. Let's speak about the unit we use in not radioactivity, but in radiation protection, and it will be useful for material irradiation. The first unit is a physical unit. It's the energy which is deposited in the material. So it's what is called absorbed dose. The official unit is gray. It's 1 joule deposited in 1 kilogram. From a thermal point of view, it's completely ridiculous, 1 joule. But in fact, for irradiation, it's huge. It's a large unit, the gray. Then, for radiation protection purpose, we can define different units, which will be useful to understand if we are safe or not when we perform material irradiation by taking into account the type of particles. For instance, the alpha particles have more impact. Okay, so we define another dose, which is expressed in sieverts, and we can also extract another dose, also in sievert, to take into account a specific risk depending on the organ which is irradiated. In fact, these two doses are useful to evaluate material damage, either inert material or biological tissue. And this damage enable us to know what will be the deterministic effect on biological tissue. This dose is only useful for long-term effect on biological tissue because inert material don't have this kind of effect. So here we are talking about cancers, all this type of funny things. Okay, what is important for material irradiation is obviously the first one. For radiation protection, we are centered about the human body, and the human body is mainly water. So the dose is usually calculated by absorption in water. But for material irradiation, and particularly for electronic circuits, we will speak about silicon, and it will be the dose absorbed in silicon material. So silicon have not the same properties as water. It's more dense, etc. So it's not exactly the same thing. That's why the dose will be expressed in gray silicon or rad silicon. So I precise that because you guys like to use a very old unit, which is the rad. So it's a radiation absorbed dose, and it is based on old energy unit, which is the erg. So a rad is 100 erg absorbed in 1 gram. And the condensation factor between gray and rad is a factor of 100. And this is this rad unit which is used in material irradiation. And I want to advise you to switch to the new world with the gray, but okay. So just to have order of magnitude in mind when we speak about radiation protection. So I give you here a scale of doses, and from 100 nanosieverts, which is quite low, to 10 sieverts. So I just put on this scale what is the natural background. So in 1 hour in this room, we will take this dose in 1 day, in 1 month, in 1 year. This is the order of magnitude, for instance, one year of natural irradiation. I can give you the limit in France. I do not know the limits which are applied in Japan, but in France, the limit for non-exposed worker is 1 millisievert. The public for let's say exposed worker is a little bit higher, but you see that in fact limits are here to protect the worker by being sure that you do not take additional radiation more than the natural radiation. I also put some biological effects. So recent studies show that the very first epidemiological evidence starts from here, but the real symptoms are here. There are several orders of magnitude above the limits which are applied. But this is for radiation protection. In fact, when we speak about material irradiation, we speak about order of magnitude above that. The doses for material irradiation are very, very high. So high, it can even affect inert materials. Inert materials are very resistant to radiation compared to us. Okay, so now let's speak about the core topic, which is radiation-matter interaction. And I will go through the different radiations, the different particles we can use to perform material irradiation. So I start with the first one, which is alpha particles. And I will detail different properties. So the emission of alpha particles, they come from heavy unstable nuclei. For instance, you have plutonium nuclei, which will decay in uranium nuclei by ejecting a part of the nucleus, which is called an alpha particle. The energy of this alpha particle is just the difference between the two energy states. It's basic physics. So you have here an example of a scheme, and you have this energy difference, which is taken by the alpha particle. The typical energy of alpha particles for radioactivity is 4 to 6 MeV. So million of electron volts. There is another process. We can just take helium, we remove 2 electrons, and then we obtain an alpha particle because it's only the nucleus of the helium atom. Depending on the size of your accelerator, you can obtain energy from, let's say, 1 to 50 MeV. So the feature of this particle is its charge, it's 2+, and it's considered as a heavy particle compared to other radiation because it has 4 atomic mass units. So the interaction the alpha particle will have with matter is a very strong systematic ionization of the matter. There is a specificity of this interaction. There are more interaction when the energy decreases. It means that when your alpha go in the matter, it deposits more and more energy until there is no more energy left and it stops. We can also say that it may scatter on the nuclei, not just on electrons. So if I speak about the range is the length the alpha can go through matter. So for instance, in silicon, if I take alphas of 5 MeV, it's standard radioactivity, you can see here what type of path you can have, and the range is more or less 20 microns. So the range of alpha particles are very low. It's only a few centimeters in air. It can be stopped by paper layer. In fact, it's even stopped by the dead skin layer on our skin. So they are not very dangerous when they are outside of our body. And I give you here a calculation of the range for different energy, but you can see that it's quite low. I will take the same scale for other particles. Okay, let's speak about another one, which is what is called the beta particle. In fact, the beta particle is an electron, but emitted in a specific process, which is the beta radioactivity. So the emission is during the decay of a nuclei in another one. When you have too much neutron in a nuclei, you have a decay to obtain more stability. The energy is, this is the same principle. It's the difference in nuclear states. But there is a third particle which is emitted. It's the neutrino. The neutrino is completely not interesting in our talk because it do not interact in matter. But the energy sharing between the electron and the neutrino makes that the electron emitted, the beta, do not have exactly a specific energy. So you have a broad spectrum of energy for the electron emitted. The feature of this beta particle is it has a negative charge, it's an electron, it's very light, okay, 3 orders of magnitude below the neutron or protons. The emission will be systematic but quite weak. There won't be really a bright peak. This rise in ionization at the end of the path, and it makes also a nuclei at low energy. And you can see that it do not look like what we had with alpha particle. It's spread everywhere. Okay, the range. There is a specific range, like alpha particle. There are a lot of scattering. Typically, the range are few meters in air and few millimeters in standard material, silicon, plastic, biological tissue. You have the range calculated here with the same scale as before. Okay, for beta particle, let's speak about the third radioactive process, which is the emission of gamma rays. So it's emitted from excited nucleus. So after having emitted your beta particle, you have still energy left, and you emit gamma rays to get rid of this energy. It's typically of the order of 1 MeV. You can have multiple emission by a single radioactive process. The feature, there is no charge, it's a photon, there is no mass, so the interaction will be weak and random. Okay, there are several processes depending on the energy. If you are at low energy, the photon, the gamma ray can be captured. If it's at higher energy, it can just scattered on the electrons. At higher energy, it can create antiparticle. But okay, mainly we will have Compton interaction, which is a simple scattering. So the range will be quite large because it's a random process. So gamma rays penetrate through matter very easily, and in fact, there is not a specific range like for alpha or beta particle. For alpha or beta particle, if the range is I don't know, for alpha particle 20 microns, you know that at 30 microns you will have nothing. Here, you can just define an attenuation factor for the flux, because you can still have gamma rays going through a large thickness of material. So you have for different material, different attenuation coefficient, all that stuff, and you can define the range with that. And I give you some example of range for 1 MeV gamma rays. So in the air, you only lose 1% of this gamma rays in 1 meter of air. For water, it's 7% for 1 centimeter. For silicon, 15% for 1 centimeter of silicon. It's way above the thickness of electrical circuit. So it's more or less transparent for very thin thickness. Okay, for gamma rays, let's speak about neutron. Neutron is very specific particle. It's not emitted in natural process. Let's say not on Earth in high atmosphere. Yes, but not on radioactive process. So it's emitted from very excited nuclei. So we can produce neutron in accelerator. We will undergo nuclear reaction to produce a neutron of the order of 1 MeV. You can have different reaction to go above this energy also. you have the fission process where uranium-235 can split and emit neutrons. The energy is more or less the same. From cosmic particles, you will have energy much higher, up to 100 MeV. So this neutron, it doesn't have charge, but it's quite heavy. It's 1 atomic mass unit. So the interaction with matter will be very weak because there is no charge, and probabilistic because, in fact, the neutron, it does not interact with the electrons. It has to touch directly the nucleus. So it's a rare event. So it means that the neutron will go through matter very easily, like the gamma ray, even higher. So you can have different type of reaction with the nuclei. What is important, it's often scattered by nuclei. It means that the neutron will not go just in straight line. It will scatter and move in different direction, and it can lose energy up to the thermal energy 25 milli-electron volt, whereas the other particle, we do not speak about a gamma ray of 1 keV. There is no meaning about that. But a neutron, it's still important, even if it has a low energy. And okay, I just give you an example of what we call a cross section. It helps to calculate the probability to perform an interaction. And you can see you have a lot of decades of order of magnitude of different energies, and neutrons, even in thermal neutrons, are still important. They can perform a nuclear reaction. So the range of such a particle, it's calculated more or less the same way than for gamma rays. You have here some cross section. It's for other nuclei than the slide before, but you have major isotopes, for instance, silicon, and we can use that to calculate the attenuation of the neutron flux. So the range are very large, and it still continue after the interaction. It is often scattered. So I give you here the attenuation with different material, but okay, like for gamma rays, it's very difficult to stop neutrons. So it's continue to spread. Last particle I present is the proton, the simple proton. It's not emitted in a radioactive process. There is no process which can emit it from natural radioactivity. So we can produce them in accelerator by stripping an electron from a hydrogen atom. And the energy of the proton is given by the accelerator. It's let's say few MeV for a small accelerator like we have in our lab. You can have proton coming from cosmic particle. In fact, it's the main component of the cosmic rays, and the energy can go up to 1 joule. And for a particle, 1 joule is just tremendous. Okay, there is not a lot of particle at this energy, but it's billion and billion of electron volts. So the feature of the proton is the positive charge. It's quite heavy. It will more or less be like the alpha particle. It will have a Bragg peak with a lot of energy deposition at the end of the path. It's more or less like the alpha particle, and I can show you this on this graph. It's proton of 1 MeV in silicon, and few slides before I just show alpha particle of 5 MeV in silicon. So you can see that it's more or less the same. It's not the same energy, obviously, but it is the same behavior. So I just make two different range. I give you two different values for accelerator protons in the MeV energy range, so a few centimeters in air, few tenths of micrometers in silicon, which will be important for materiality radiation. But cosmic protons have range they cannot be stopped easily. For 100 MeV, it's 1.5 centimeters, but for 10 GeV, it's 7 meters of lead. Nobody will put 7 meters of lead to protect from this particle. And you have here the range depending on the energy. Okay, so I just give you a scope of different particles. Let's say about various concepts of material of a radiation material interaction. So we can perform material damages. The damages will depend of the type of particle, because it do not induce the same damage even for the same dose in gray silicon or in red silicon. For instance, electron and gamma rays, as I said before, they break chemical bonds by stripping out electrons. So I just perform a quick simulation. I send a 1 MeV gamma ray beam. You can see it in red in 1 cubic centimeter of silicon, and you can see that there is a direct beam. There is scattering of gamma rays in every direction, and this beam also make electron ejection in the process. On the contrary, heavy particles like alpha, proton, neutron, or heavy ion, if they have a high energy, they can induce atom displacement. They can knock an atom and make it move, not an atom, a nuclei, and make it move to another seat in the matter. And it is called atom displacement. It is very famous in nuclear industry. For instance, for the fuel, you can have up to 50 displacement per atom. It means that every atom has been displaced 50 times at the end of the 3-year process in nuclear reactor. So the strongly interacting particle will induce greater damage because the damage will be more concentrated instead of being diluted in a longer track. So, as I said before, biological matter is very sensitive to irradiation. That's why there is 2 different topics. In fact, we are based on complex chemistry, complex molecules, and as soon as you begin to break these molecules, you can have some troubles. Okay, hopefully we have a lot of reparation processes, but okay, we are quite sensitive to radioactivity, to ionizing radiation. On the contrary, inert material can only be affected by high dose. That's why we're speaking about tens of kilogray per second. So high dose of heavy particles, which will displace some atoms. Okay, it's not very clear on these pictures, but as the dose increase, you have some structure appearing, some loop, some effect which can be seen in microscopes. Electrical circuits can also be affected by electrostatic effect. And you can have creation of charge carrier, you can have parasitic current, it will induce difference in potentials. Okay, I'm not an expert at all in this field. That's also the aim of the project we have. Okay, there was a question about activation. The activation is the process which make radioactive your sample or materials. So is it possible to have some activation in the process of material irradiation? Alors, radioactivity is due to a nuclear instability. It means that you need to change your nuclear structure to make it radioactive. So gamma rays and electrons, they cannot change the nuclear structure. So it cannot give you an activation of your sample. It really needs neutron or high energy protons or alpha particle to induce a change in the nuclear structure. But there are some thresholds. For instance, I give you cross-section, but let's speak about probability of interaction for proton and for alpha particle. If you are at low energy, your probability will be more or less 0. So you cannot activate material only if you have very large energy. In fact, the proton and alpha particles, they do not like to go inside the other nuclei because they are both positively charged. So, okay, no material activation, but with big accelerators. On the contrary, a neutron, it has no charge, so we can enter the nucleus very smoothly. For instance, here for copper, you can see that at low energy, there is not the scale, but at low energy, it's not 0. You have a large cross section, so we can enter the material and change the structure. So it depends on different parameters, typically on our facility, which is called EFIRA in our lab. When we irradiate copper targets, we will have some activation because we will transmute some copper isotope into other copper isotope which are radioactive. So it can happen, but the activation is quite low because the flux we are talking about are quite low. So for the application we have, the activation won't be a big deal, but it's something which has to be checked. To conclude, okay, as I said, ionizing radiations, they are everywhere from natural process to artificial sources. There are different origin depending on the particle we are talking about. Alpha, beta, gamma, it's mainly natural process, nuclear industry, nuclear wastes, etc. Neutron and proton, it's only from cosmic rays. So this radiation, they induce some damage on biological tissue by electron stripping and on inert material by atom displacement. And last point, this particle have different range in matter, which let's divide it into are very short for heavy charge particle and very long for neutral particle like gamma rays and neutron. That's it. Thank you for your attention. Is there some questions? Yes.
Thank you for your presentation. Considering the different range of effects of the different radiations, what would be the best type of irradiation to test maybe maximum circuits?
In fact, it's not a question of range, it's more a question of type of damage. Even alpha particle may have enough range to induce damage in the thickness of the circuit. In fact, it depends on what we want to observe and the application we want to focus about. If we want to focus about radiation hardness for planes or satellites, it's we have to deal with neutrons or protons. If we want to address the problem of robots in nuclear industry, it's more gamma rays. It's that which will drive the choice of the particle. Is it okay?
To your knowledge, is there any packaging material like
lead
for the robots that is already used, and maybe especially for packaging circuits?
So, if we are talking about robots, we are talking about gamma rays issue. And for gamma rays, you can see that for one centimeter of lead, you have, okay, you reduce your flux by 50%. It means that, okay, 1 centimeter is 50%, 2 centimeters, 75%, 10 centimeters, 1,000, a factor of 1,000. But if your flux is very high, 1,000 is not enough. So, and you cannot put 10 centimeters of lead around your robot everywhere. Lead has a density of 11. It's very dense, it's very heavy, and you cannot do that for to protect your robot from gamma rays. You can protect it from, let's say, low energy gamma rays, beta particle, but it's not a viable solution. Depending on the gamma flux where you are, where you want your robots to go, but it's not a good solution.
I have one question. I don't understand why the attenuation depends on the energy.
In fact, because the physical process depends on the energy. When the gamma ray has a low energy, it will be, in fact, it will be captured by an electron. So it's not just basically that the gamma ray has to touch the electron. If you have a low energy, your attenuation factor, your coefficient is very high. As soon as you are close to the electron, it will be captured. So it completely depends on this energy.
Any other question? So thank you. Thank you again. So we will now have the poster session, but before that I have some present for the talkers.